Next, we're going to cover the mean value theorem. Now, the mean value theorem is a very important theorem in calculus, and we're going to see that we can use it to understand more about how the derivative behaves as you travel through a curve. But first, in order to build up to the mean value theorem, we're going to consider a special case of the mean value theorem called Rolle's theorem. And I'll explain why it's a special case in a moment. Rolle's theorem. We have three assumptions. Let f of x be continuous on the closed interval a to b, and differentiable on the open interval a to b. It doesn't have to be differentiable on the boundary points. If f of a equals f of b, our third assumption. So we have continuous, differentiable, and the function is the same at both endpoints. So the y value is the same at both endpoints. If f of a equals f of b, then there is some c in a to b. Now this symbol here, you've probably not seen before. It's like a, I don't know, kind of like a curvy E. But it's red, just the word in. And in math, it's used to pick out an element in a set. So there's some c inside the open interval a to b, such that f prime of c equals 0. So the conclusion is there's a point in the middle, or well, somewhere in this interval, where the derivative evaluated at c is 0. So let's see what this looks like on a graph. We know what derivative being 0 looks like on a graph, horizontal tangent, but let's see how these assumptions get us to that conclusion in this example. So we have continuous, differentiable, f of a equals f of b. So let's mark off an a and a b, and f of a equals f of b. So they have the same, so the function has the same y value. Well, we need it to be continuous and differentiable, so we need to connect these dots, and we need to avoid corners and cusps and vertical tangents. Well, we can do that like this. Right here, we have a function which satisfies the three conditions, the three assumptions of Rolle's theorem. So since it does satisfy those assumptions, then there must be some c value between a and b where the derivative is 0. Well, where would that be? Where is a horizontal tangent? At that c value, the tangent line is horizontal. So how should I say it? In this case, there's 1. So I'll just say the c value. Maybe I'll say it a little differently. F, let's call it c. F prime at c equals 0 at that x value. So right there, in this curve, there is some c value where the derivative is 0. Now, if it's not continuous, you could break apart the graph so that there's no point where the tangent line is horizontal, even though f of a equals f of b. But let's look at why it doesn't necessarily hold if the function is not differentiable. And let's look at, maybe I'll, here. Let's say here, f prime of c equals 0 here, at that x value. But why does this theorem not necessarily hold if the function is not differentiable? Well, let's look at this curve. F of a equals f of b. It's continuous, not differentiable. So here, let's call this f of x. There is no value where there's a horizontal tangent line. Remember, at that point, the tangent line doesn't exist because on this side we have positive sloped tangent lines. On this side, we have negative sloped tangent lines. The derivative at that top point doesn't exist. In particular, it's not 0. The derivative everywhere else is also not 0. So here, this here and this there look remarkably similar. This is here and this is there. So here, there is no value where, there's no value c where f prime at c equals 0. There's no horizontal tangents. And, you know, this theorem says that we're guaranteed to have 1, and you may have more than one such c value. I'll just draw a curve right here as another example. F of x has 2 c values as in Rolle's theorem for this curve. So right here we're going to demonstrate a function where, you know, there is more than one c value. F of a equals f of b. Well, it could look, okay, let's call it 3 c values. There are 3. You know, to make it 2, you could have gone lower under here. But right here, there are 3 such c values because we have 3 horizontal tangents. So I'll call them C1 right here, C2, and C3. But Rolle's theorem doesn't say there are necessarily 3. It does say that there is at least 1. Now, Rolle's theorem is, well, there are 3 assumptions on Rolle's theorem. And Rolle's theorem is a special case of the larger mean value theorem. And to get to the mean value theorem, we're going to take away this assumption that f of a equals f of b. And the mean value theorem, if f of a isn't going to equal f of b, well, f of a is going to be, say, here. F of a will be, say, here, at that height. F of b will be, say, here. Well, the Rolle's theorem conclusion is still going to hold if you connect them in the same way. You just have to tilt it on its side. So let's take a look at that. The mean value theorem. Here, I note in a parenthetical, we remove the assumption that f of a equals f of b from Rolle's theorem. So our only assumptions for this theorem, let f of x be continuous on closed interval a to b, differentiable on the open interval a to b. Then, there is some c in a to b such that blank. Well, let's fill in that blank. Let's try to construct the end of this sentence. Mark off a and b. F of a doesn't necessarily equal f of b here. So we have f of a, we have f of b. But we are going to connect them in a continuous and differentiable way, meaning it's going to be in one piece, and we aren't going to have corners or cusps or anything like that. So let's see, how can we do that? Let's make it look like, how do I want it to look? I'm going to move b down a little, move f of b down a little. Yeah, that's not that good of a drawing. F of A, f of B. How did I draw it over there? I like the drawing in my notes. Okay, it looks kind of like a roller coaster. No, I don't like that. It'll be easier if I don't mark off f of B. There, okay. So f of B, somewhere up here, f of A over here. It's one piece, no corners. Then there's some c in a to b such that what? Well, what did Rolle's theorem look like? Well, Rolle's theorem said if f of A equaled f of B, then there's going to be a point in the middle, where the tangent line is horizontal. But let's put another line here between f of a and f of b. Rolle's theorem said if f of a and f of b are on the same horizontal line, then somewhere in the middle you're going to have a point where the tangent line is parallel, or is horizontal. Both are horizontal. Another phrasing of Rolle's theorem could be that somewhere in the middle you'll get this pair of parallel lines. Well, mean value theorem just says we can take this and tilt it on its side. We're still going to get the same pair of parallel lines. That's what the mean value theorem is going to say. How can we see this horizontal tangent? Well, you can let a line travel through it. Let's do the same thing here. Let's construct a line between a and b, or f of a and f of b. Well, there's the line. Somewhere in the middle, we're going to have this same set of parallel lines just tilted. And do we? Well, let's take a look. Well, right there, that looks awfully parallel. And after that, it's not going to be. So Rolle's theorem, tilted on its side, gives us this pair of parallel lines. And right here is going to be the corresponding c value. Now, how do we turn that? Maybe I should call this example. Example. Illustrating mean value theorem, commonly abbreviated MVT. Now, the Rolle's theorem argument said we have these parallel lines, and the conclusion was actually saying the slope of this line up here is the same as the slope of this line down here. Slope of this line, f prime of c, slope of this line, 0. Well, we have the same situation here. Slope of this line up here, derivative at c. So such that, let's put it here, the derivative at c equals what? Well, what's the slope of this line? Well, we have 2 points on the line. So the slope is the change in y over the change in x. So mean value theorem says let f be continuous differentiable, then there is some c inside a to b such that the derivative at c equals f of b minus f of a all over b minus a. And that could be rephrased using parallel lines on a graph like this. And the mean value theorem tells us a lot about the behavior of a function on a closed, well, it tells us a lot about the behavior, sorry, I got distracted by this ladybug up here. The mean value theorem tells us a lot about how we can interpret the derivative of a function on intervals. And it tells us about how the derivative travels through a function. Now, there are many applications of it. We're going to see a few consequences of it in a moment. But first, let's consider this example. Example. A rock is dropped from a height of 100 feet. Its height above ground t seconds later is given by s of t equals negative 16t squared plus 100. And what do we have? 3 parts. When does the rock hit the ground? Find the average velocity during the fall, both of which we could have done before mean value theorem. Part C, find the time at which instantaneous velocity equals the average velocity. Now, we actually could have done all 3 parts of these before the mean value theorem. But once we get to part C, I'll explain more about that. When does the rock hit the ground? Well, you drop a rock. The function gives its height above ground. So we want when it's 0 feet above ground. So we want to set s of t, what was it? Plus 100. We want to set s of t equal to 0. Well, solve this, what do we get? T squared is 50 over 8, 25 over 4. T, I didn't write a domain restriction for t because technically we're going to be finding it here. Only the positive will take. So this ball is in the air from second 0 to second 5 halves. Part B, find the average velocity during the fall. Well, I just said the ball is in the air from time 0 to time 5 halves. It starts at time 0, it's on the ground at time 5 halves. So we want the average velocity on, so we want VAV on 0 to 5 halves. And how do we find the average velocity? Well, it's the change in position divided by the change in time. Well, conveniently, we already found up here that the position at 5 halves was 0. S at 0 is what? 100 divided by 5 halves, and 100 times 2/5 is 40. And there's a negative on that. So we get negative 40. What are our units? Feet and seconds, probably? Yeah. Feet per second. And this is seconds. Now, part C, find the time at which the instantaneous velocity equals the average velocity. Well, that's another way of phrasing the mean value theorem. Because remember, the average velocity corresponds to the slope of a secant line. The instantaneous velocity corresponds to the derivative at a point, if you have a position function. So we're looking for where the derivative at a point equals the slope of a secant line. Well, we're looking for exactly this diagram, we're looking for this visual, and we're trying to find the value in the middle where that is true. So in part C, I'll just write, before even doing the answer, such a value, such a time, exists by the mean value theorem. That's a period, not a comma. So we have to find that value. Find the time at which the instantaneous velocity equals the average velocity. Well, we need, well, here's the average velocity, negative 40. We need where, need spelled with a D, where, what is it, S prime of t equals negative 40. So let's find S prime of t. We have negative 32t plus 0 equals negative 40. Solve for t. You get t equals 5/4 seconds. And in this situation, just a ball dropping, t equals 5/4 is exactly in the middle. So we're going to see a couple corollaries of the mean value theorem in the next video. And we're going to use those corollaries. Well, actually, we're going to see 3 corollaries. A corollary is a small, immediate consequence of a larger result. So we're going to see 3 immediate, small consequences of a larger result, the mean value theorem, at the beginning of the next video. 2 of them we're actually not going to see again for 2 weeks, but the third of them we're going to use to figure out how we could sketch a graph of a function just using calculus.